Hello, and welcome back to my Breadboard 486 project. Before I dive into anything today, a minor correction. In the previous episode, I referred to this little guy, come on, focus, as a Zener inverter. But there's no such thing. It's a Schmidt trigger inverter. A Zener is a type of diode. I'm not entirely sure how it's different from a normal diode, to be honest, but it's a type of diode. Now, if anything, this kind of shows that I only sort of know what I'm talking about. So it's best that you take anything I say with a little bit of a grain of salt and trust but verify. So, yeah. All right, on to the project itself. Now, I originally said I was going to work on the UART this episode, and unfortunately, I have been sidetracked on this one because of an issue of time, but not available time. Now, the issue... Okay, quick aside. These breadboards are awful. Just terrible. They have no grip once you use them a couple times. I mean, look at that. It just barely holds on. So yeah, these are absolutely horrible breadboards. I'm actually going to get rid of them sooner rather than later. But I'll talk a little bit more about that in a moment. So, the problem. Let me turn this on. All right. You see how we have this wonderful set of 4 lights? 66 hex. This is not the right value. It should not be displaying that value. In fact, that value exists nowhere in code. And in fact, if you actually slow it down, it's actually at 2244. But yeah, that value doesn't actually exist anywhere in code. So, let me bring up the actual code here for a moment so you can actually see what's going on. Okay, so this is the code that's currently on the ROM. It's pretty straightforward. All we're doing is we are setting AX to 2288, and then we're saying BP to 1144. We're writing BP to address 4, and then we're writing the value of AX. It's not really the value of AX. Experimentation was happening to figure out what was going on, but we're taking the value 2288 and we're writing it to CS0, the code segment 0. This means we're actually writing it into the ROM. Now, why did I do this? Mostly to prove that it wasn't about enabling the memory chip, that it was unrelated to that bit of logic. So the point is, we issue that write, and then we immediately read the value that we had of BP. A no-op, once again for timing, and then we compare it to what BP should be. And if it fails, we just take that value and output it. Ignore what I was just about to say. We output it to E9. Straightforward there. If it succeeds, well, we output 21 to E9. And then we go back and we do the reread just to confirm that the ROM has been corrupted. And that's the magic for this, is this particular order. It needs to have this arrangement. And that's what's causing this problem. Now, the net result of all that is that we're corrupting RAM. And the whole idea that the act of reading RAM causes it to be corrupted, that's not a good thing. Now, I spent a couple of weeks pulling my hair out on this one. And even when I thought I had a solution, it turned out I didn't have the solution, or rather I had a bad solution. Now, the real solution can be found in the datasheet, because, what else can't be found in the datasheet? So we are back to this wonderful thing, our timing chart. Because the problem is about time. So, let me just use this. If we look at the way the bus cycles work, the address data strobe, or address data latch, or whatever you want to call it, I can never remember the appropriate name of this signal, I apologize. When it goes low, that indicates that the address bus the address information, which is going to be the address bus, MIO, DC, WNR, and BE0 through 3, are valid. Now, we use this to indicate that, when ADS is low, we are doing address processing, and when it goes back to high, that's when we do data processing, because, it reads and writes to the bus only when it's high. So we can see that. This is great. It works just fine for the most part. The problem comes about, as I said, timing. And this is irrelevant to the clock speed. I could be clocking this thing at 1 cycle a day and this will still happen. Not that you could probably do that, but you get the hyperbole. What's happening here is that in this time period here, right about where the brown line is right now, it's updating the address lines, but ADS is still high because it hasn't set all the values yet, and memory read-write, as well as I/O, is set to the previous state, which means that we write, and then in the process of reading, it puts the address we want to read from on the address bus. And there's a tiny fraction of a moment between when it does that and it sets the read-write line to be reading. But in that fraction of a moment, it writes to the data, writes to the bus. Now, I would love to show you an oscilloscope capture of this, but my oscilloscope is kind of a low-end model. It has 2 inputs, no video capture, and I'm not entirely great at using it yet. I'm kind of terrible at using it for the moment. Yeah. Luckily, there's a very simple solution to this problem. I almost said a problem to this solution, which is probably correct, but not the way I intended. And that is to latch the data related to the address and bus and the address bus. And we do that with just a couple latch chips. It's actually a surprisingly simple circuit. This is the one I need to build for the board as it sits. We need an inverter. It takes in the ADS signal and inverts it. And that is because it feeds into each latch chip, and the latches are latched on high, at least the chips I have. The output's always enabled. We're just constantly pushing the data back out. And, we have one chip for the first 8 bits of the address bus, which includes address line 0 and 1. And then we have another one for the next 8 bits. And the third one is grabbing A31 and the MEMIO, DC, and read-write lines. Now, I'm not bothering with the byte enable lines because those are being captured with A0, A1. And I'm also not bothering with the byte enable low, byte enable high lines, byte low enable, byte high enable lines that are used in 16-bit bus. Because this board is only doing 8-bit, so I don't need to worry about that. Now, when I actually go out and build the full breadboard, I'm going to need 6 latch chips. Though 2 of them are mostly going to be, only about half used. In fact, the support board that I've been designing has gotten a lot more complicated because we have these 6 chips. We have like 4 chips for generating the various signals for the bus types. We have 8 different ones for bus routing. It's a very complicated board. Well, not very complicated. It's actually fairly straightforward. It's just dense. But that's another show. So yeah, now I need to build this. Let me just pull this away. Now, the latches I'm using are going to be 47573. Let me just lift this up a little bit so you can get a good view of the data sheet. All right, there we are. So yeah, they're very nice in that, much like with the address bus chips, the data flows in a single direction. It flows from the left side when it's up, from pin 1 side to the right side, or the pin 20 side. But just like I actually do this in view, the bus driver chips here we need to put them backwards on the breadboard for the optimal placement. We want it to have, and let me grab my breadboard. We want the data, the input, from the address, from the CPU, be on this side of the board, and the output on this side of the board. Because the plan is to slip it here, between these two boards on the bus. So we have the data processing, the address processing, and then we have our RAM and ROM. Sorry, ROM and RAM. So yeah, that's the thing we're going to have to do. But rearranging the board is going to go wait till later. Now, cycling back around to breadboards, I did pick up some of these breadboard.com breadboards, and for the most part, I like them. I'm not too terribly fond of the numbering being upside down, because as a general rule, I prefer the power lines to be low. You know, it makes it so you can just do short jumpers between the power and ground on the standard chip arrangement. But yeah, but that's really a mild problem. Honestly, it's not a big issue. So, okay, let's just get this built quickly. And the good news is that this is a very simple. There we are. Pop that in. Get my ground and power. Yeah, very simple board. It's actually mostly just power connections, surprisingly, plus a little bit of control lines. So let's see. Latch enables on pin 11, so put that there. Then put the next one right next to it. There we go. Now I want to have ground on this side, and I also need to tie the output enable line and power on this side. And there. Okay, that one's done. Yeah, this is really a straightforward set of circuits. It's a plumbing circuit is the best way to describe it. So yeah, I can't think of anything better to say other than that's a plumbing circuit. But that works for what it does. I mean, that is a plumbing. I need to, it's piping data around. So that here. Okay. Now I'm leaving a large gap here so the data bus can go down between the address bus chips. So that's kind of why this arrangement is the way it is. All right, so the inverter, make sure that's on the output. I love the click on these boards with the chips. They just, that is so nice. They just slide right in. That's beautiful. All right, there's the ground. There's the power. Make sure I actually get it hooked up correctly. Double check that. I have been lately misaligning my power jumpers, so I need to start really double checking those because it's embarrassing. And it's like, why isn't this working? Because I didn't plug it in correctly. Yeah, competency, not my middle name. There we are. There's that one. All right, and so the last ground lines, that gets grounded. That gets grounded, and then this connects to power. And that should do it. I mean, seriously, this should be the entirety of what I need. Double check my power connections. All right, yeah, everything looks good and looked just as good as it did last time I did it, but all right. Now, wiring this up is going to be a bit of a mess. I apologize for that. As I said, I'm going to have to rearrange the board later. I'm not going to do that on camera because, let's be honest, you saw me build it the first time. I don't think you want to see me tear it apart and put it back together. I mean, it would just be like a 10-minute long fast forward. So, not exactly the most exciting thing in the world. Okay, so need to run these over the top like this, even though it's ugly, because I need the extra room. Okay, ground, power. All right, those are there. Okay. Now the awkward placement of wedging these in sideways on one side and this one on the other. Come here. All right, double check my alignment. That's good. Make sure those are there. Okay. And then lastly, for the moment, we'll just pop it right onto the ADS line. So next is to make sure it actually works so far. Make sure I didn't screw it up. So if all goes well, we should actually see some interesting data. Plug it in and turn it on. And there, would you look at that? 21. That's correct. That is the data we should be seeing. That's the data we're reading from the memory and what we're expected to do. Now, why is it working now when I only have the address buses and the latch? I personally think it's just the little delay the latches add. I don't know how long that is, and I'm not entirely sure how to read the data sheet to find out. But I think that little delay adds just enough time to make things synchronize correctly. But that's coincidental synchronization. I don't want that. I don't want to work just because I got lucky. Because, I do that already enough. I don't need to keep doing that. So, put the data lines there, put the address line there. Now, address line is purple. And yes, this is, don't pop out on me. Silly breadboard. And yes, this is a mess, and I apologize for that. As I said, I will have this cleaned up before the next episode. Assuming, of course, that I don't accidentally screw something up in the middle while setting all this up and manage to botch it completely. Because, that sort of thing happens. Yeah, this has been not the easiest one to record either. Okay, so that should continue to work. Oh, look, it doesn't. Oh, didn't I warn you? Make sure those are right. Oh, I see what I'm doing wrong. I have them backwards. I am so good at this, aren't I? Really good. That's the downside with having this arrangement and having it be sort of reversed of where I would naturally have it if the chipboard was here, is that I keep wanting to put the things in backwards. All right, and there we go. That did it. Back to 21. And that's it. That is the fix for the timing issue. Now, the UART isn't going to be much more complicated than this, but I want to get the board cleaned up before I go much further. It's easier to explain what's going on, and it's just easier for you guys to actually see what I'm doing. Because, let's be honest, this is a little bit of a mess. What I should also do is I should actually eventually replace this with a hex LCD, an actual 7-segment LED, not LCD. I mean, I have an LCD, but it's a pain to wire that up. I have a little microcontroller that can generate hex signals for a 7-segment display, so I should wire that up and just make it a little easier to read than just random dots of light. But luckily, they are the correct ones, and this seems to fix the issue with the memory. So now everything seems to be correctly synchronized. We latch the address data, and when we're latching it, this is disabled. So that's a nice thing. So we have that. There's a nice guarantee that all the control lines are all high when we're changing the address data, which means that they should always be cleanly separated. I have no idea if that's going to be true or not. We will find out as I go along. But yeah, so that is, that's, I think, it for this one. I think that wraps me up. And, I don't know what else to say. I just keep saying, which is not the best filler word in the world. All right. Well, thank you for being here. Thank you for watching. I hope you enjoyed this particular episode. I hoped it made sense, because this was a head on the wall for me for quite a while to figure out what was going on. My first instinct with this problem was the wrong one. If you do a lot of software developing, you're going to run into a bug where your first thought is, oh, the problem is the compiler, or in this case, the problem's with the chip. You are wrong. That's going to be your first instinct, and you are wrong. The problem is not with the compiler, the problem is not with the chip. That being said, occasionally the problem is with the compiler or the chip, but this is too common of a control path for that to be the problem. There are bugs in the chips. Every Intel chip has bugs. The classic F00F bug on the Pentiums that caused them to crash. Lots of bugs. Most of them are minor. They don't, and you're usually told not to do certain things to avoid them. But there we go. There's your thought for the day. It's never the compiler's fault, except when it is. And I've actually run into compiler bugs before, though usually always related to optimizations. And I have gone so far off track. Okay, well, thank you for watching this episode. Thank you for coming and enjoying the series. I hope you liked it, and I'll have another one again soon with the UART, hopefully faster than this one was. So, thank you, and good night.